Welcome to the deep dive. This is where we really get into the weeds on complex topics, pulling out those key architectural ideas that shape the world, often in ways you don't even see.
Yeah, and today's topic is a perfect example of that. We're looking at what you could call this massive, invisible empire of computing.
It's everywhere, isn't it?
Absolutely everywhere. I mean, right now, wherever you are, you're almost certainly surrounded by dozens, maybe hundreds of tiny computers.
In your microwave, your car.
Your thermostat, your washing machine, even your electric toothbrush sometimes. They run diagnostics, regulate engines, process signals in your phone.
And the sheer volume is staggering. They make up the vast majority of processors sold, yet the way they're designed, it's completely different from the laptop or phone you might be using right now.
Totally different rules.
Yeah.
We obsess about speed on our desktops, right? Getting the highest benchmark.
Yeah, max performance.
In the embedded world, the game is different. It's about hitting the minimum performance needed reliably and, crucially, at the lowest possible cost.
So these are embedded systems, and yeah, their scale, their design, it kind of turns everything we think we know about performance computing on its head.
Our mission today, then, is pretty straightforward. We want to get under the hood and understand why. Why are these systems built using approaches that sometimes actively reject the very features we value most in our general-purpose computers? And to figure that out, we've pulled together insights from a range of sources looking at the unique pressures on this market. Things like real-time deadlines, which are absolutely critical.
Can't miss those.
Nope. And extreme power efficiency needs. We'll also break down some specialized architectures like digital signal processors or DSPs.
And we've had some really cool case studies too, right? Like the PlayStation 2.
Oh yeah, the PS2's Emotion Engine is a fantastic example. It really shows how fragmented and purpose-built these systems have to be to cope with these intense demands. We'll also look inside digital cameras and cell phones.
Okay, so I think the place to start has to be the scale. Because, like you said, we focus on desktops, maybe servers, but that's just the tip of the iceberg. The embedded world is, well, it's enormous. It's absolutely enormous, and understanding that scale is crucial because it dictates the economics.
Yeah.
You know, the sources are clear. The embedded market is, hands down, the fastest growing part of the entire computer industry, faster than PCs and servers combined.
By a huge margin,
Yeah.
especially in terms of unit volume. If we take a snapshot, say, back around the year 2000, which was a key time, roughly 300 million 32-bit and 64-bit embedded processors were sold globally that year.
And those are the relatively powerful ones, right? Like for networking gear, maybe printers, that sort of thing.
Exactly. The more complex embedded tasks.
Yeah.
Now, compare that 300 million. In the same year, the world bought about 150 million desktop PCs.
Okay, so double the number of embedded chips already, just counting the higher end ones.
Both the desktops
Okay.
and servers. Only about 4 million units sold that year. So embedded was already dominating the volume of, let's say, a series of processors.
What?
But here's the number that really drives it home. If you add in the simpler 8-bit and 16-bit microcontrollers, these are the really cheap ones doing basic tasks, like controlling a single motor or reading a sensor.
The ones that cost maybe pennies?
Sometimes literally pennies, or less than $1, yeah. If you include those, the total number of embedded processors sold back then topped 1 billion units in that year alone.
1 billion compared to 150 million desktops. So what's that, like 6 or 7 hidden computers for everyone we actually saw on a desk?
Pretty much, and that completely reframes things. It explains why the sources say the biggest selling microprocessor of all time isn't some fancy Intel Core i9 or whatever.
It's probably some little 8-bit chip.
It's an 8-bit microcontroller from Intel, according to the material, that tells you where the real volume, the real economic gravity lies in this industry.
Okay, so that massive volume, especially at the low end, must completely shape the design philosophy. It's the #1 factor. It leads directly to the core principle. Economics trumps raw power, always. The price range here is just vast, you know? Less than $1 for those simple 8-bit guys, up to maybe hundreds of dollars for really high-end embedded chips in, say, complex telecom equipment or industrial robots. Whereas on the desktop, we're kind of conditioned by Moore's law, right? We always want faster, and we'll generally pay more to get it.
We definitely will.
Yeah.
But in embedded, the goal is fundamentally different. It's explicitly about meeting the performance need, whatever that specific need is, at the absolute minimum price.
Not about exceeding the need.
No, why would you? Achieving higher performance at a higher price is actually seen as a design failure in many embedded contexts. Price is king. If an old cheap 8-bit chip can reliably blink an LED or read a temperature sensor.
There's zero reason to use a faster, more expensive 32-bit chip for that job.
Zero market incentive.
Yeah.
Performance just has to be good enough for this specific task.
And because that task is so specific, I mean, a microwave processor only ever needs to run microwave logic. The whole system can be really tightly tuned.
That's the other huge advantage. You're not building a general-purpose machine that needs to run software someone hasn't even thought of yet.
Like my laptop has to.
Exactly. In a lot of embedded systems, the software is fixed. It gets loaded once at the factory, maybe gets a firmware update once or twice in its life, if that. So the application code is, as the sources say, carefully tuned for the processor and system.
Does that tuning ever involve going down to, like, assembly language?
Historically, yes, quite often. Especially in really performance-critical or time-sensitive loops, engineers would drop down to assembly to squeeze out every last cycle, save every last byte of memory.
Is that still common?
It's less common now, mostly due to, time-to-market pressures and the complexity of modern systems.
Yeah.
C and C++ are much more prevalent. But that philosophy of optimizing for the specific hardware, of getting maximum efficiency from the chosen silicon, that absolutely persists.
Okay, so if you're an engineer starting a new embedded project, maybe designing that temperature sensor controller, the sources say there are basically three main architectural paths you might take. What are those?
Right. The choice really depends on the specific needs, the performance targets, the cost constraints, all that.
Makes sense. So approach one is the most custom route. You combine a standard processor core, maybe an ARM core or a MIPSys core, something licensed, with your own custom hardware logic. This is an application-specific integrated circuit, or ASIC, and often they put both on the same chip.
Exactly. That's a system on a chip, or SoC. You design custom hardware for the really specialized high-speed tasks that software alone couldn't handle efficiently, and you integrate it right alongside the standard processor core. Maximum integration, minimum components.
Okay, that's the high customization route. What's next?
Approach 2 is much simpler, hardware-wise. You just take a standard off-the-shelf embedded processor, one you can just buy, and you run your own custom software on it.
So all the differentiation is in the code.
Pretty much. You rely heavily on software optimization, careful coding, maybe choosing a processor with just the right peripherals, but the chip itself is standard.
Got it. And the third way?
The third path involves using a digital signal processor, a DSP, along with custom software. This is the choice when your main job is processing continuous streams of data, like audio signals, video, radar returns, sensor readings.
Stuff that involves a lot of math on incoming data streams.
Precisely. DSPs are specifically architected for those kinds of repetitive, mathematically intensive signal processing algorithms. We'll definitely dig more into DSPs later. All right, let's get into what I think is the absolute core difference between embedded and general-purpose systems. These things called real-time constraints. This is where, like you said, predictability suddenly becomes way more important than just raw speed. Yeah, this is fundamental mind shift. Most embedded systems operate under deadline-driven constraints. A specific calculation must finish by a specific time, or else the system fails. And failure here isn't like, your web browser hangs for a second. If the computer controlling your car's anti-lock brakes misses its deadline.
That could be catastrophic, exactly.
Yeah.
So we usually talk about two types: hard real-time. There's an absolute ironclad deadline. Maximum execution time is fixed. The classic example is processing video frames in a set-top box. You have to process each frame before the next one arrives, maybe every 33 milliseconds for 3050's video. Miss one, glitch, that's a failure. Okay, hard deadlines. What's the other type?
Soft real-time. Here, missing a deadline occasionally is okay, maybe not ideal, but not a total system failure, as long as the average time is met and you don't miss too many in a row. Think maybe dropping a packet in a voice over IP call.
Annoying, but the call usually survives.
Right, it degrades gracefully, hopefully.
Okay, so hard real-time is the really tough one. And this is where, and I find this fascinating, the very architectural tricks that make my laptop feel fast. Things like caching, branch prediction, they actually become a problem. They become the enemy of predictability, specifically for hard real-time analysis. Think about it. Your desktop CPU gets its high average speed from making really good guesses, like predicting which way a program branch will go.
Yeah, or predicting what data you'll need next and pulling it into a fast cache memory before you ask for it. These things work brilliantly most of the time.
But not always?
Not always. Sometimes the branch predictor guesses wrong. Sometimes the data you need isn't in the cache and you have to go all the way out to slow main memory. These events cause unpredictable delays.
And for a hard real-time system, that unpredictability is killer.
It's poison. Because the system designer can't rely on the average speed, they have to design for the worst-case execution time, the WCET.
Meaning they have to assume everything goes wrong?
They have to assume the absolute slowest possible path through the code. Assume every branch prediction is wrong. Assume every single memory access is a cache miss.
Wow. If they actually calculated WCET based on that for a modern desktop chip, the number would be huge, wouldn't it?
It would be massively pessimistic. You'd calculate a required clock speed based on this nightmare scenario that might almost never happen in reality.
Which means
It means you'd have to massively over-design the system. You'd pick a much faster, much more expensive processor than you actually need for the average case, just to guarantee that even in the absolute worst case, you still meet the deadline. And that blows your primary goal out of the water, minimum cost. Completely violates it. So the solution isn't to use those fancy desktop chips and live with the pessimistic analysis. The solution is to design chips differently.
designed for predictability, not just speed. How do they do that? What do they swap out?
They replace dynamic, unpredictable features with static, predictable ones. Take branch prediction instead of complex dynamic prediction hardware.
Which guesses at runtime.
Right. They might use simple static hint bits added to the branch instruction itself by the compiler. The hardware just follows the hint. It's less accurate overall, maybe, but its timing is 100% predictable. No guessing involved at runtime.
Okay, and what about caches? The ultimate speed gamble.
Caches are tricky. They give great average performance, but a cache miss causes this huge unpredictable delay. So one approach is to just not use caches or use very simple ones. Another is to use software-managed on-chip memories, sometimes called scratch pads.
So the software explicitly loads data into this fast memory.
Exactly. It doesn't perform as well on average as a big dynamic cache, perhaps, but the latency is completely predictable. The programmer knows exactly how long that memory access will take every single time.
The sources mention a kind of hybrid approach to cache line locking.
Yeah, that's a clever compromise you see on some more sophisticated embedded chips. It lets the programmer designate certain lines within the cache as locked.
Meaning they can't be kicked out.
Right. They can't be replaced by the normal cache replacement algorithm. So you can load your critical time-sensitive code or data into these locked lines, and you know it will always be there, giving you predictable access, while the rest of the cache can still operate dynamically for less critical stuff. It essentially turns part of the cache into a software-managed memory.
That makes sense.
Yeah.
Okay, beyond predictability, we keep coming back to cost. And memory is a big chunk of that cost, right?
Huge. In many embedded systems, the memory chips RAM and flash can be a really significant part of the total system cost, the bill of materials.
So there's huge pressure to use less memory.
Immense pressure. Now, the amount of data you need is often fixed by the application, like the size of a video frame or audio buffer, but the amount of memory needed for the program code itself, that can be minimized.
Ah, so this drives choices about the processor's instruction set, making instructions more compact.
Absolutely. Architects designing embedded processors often prioritize code density. They might use variable length instructions or more complex instructions that do more work per instruction, all to reduce the total number of bytes needed to store the program. Saving even a few kilobytes of code space can translate directly to using a smaller, cheaper flash memory chip. And the final big constraint, power. You see laptops plugged in, servers in data centers with massive cooling, but billions of these embedded things are running on batteries or have no fans. Power is critical, often existential. If it runs on a battery, low power means longer life, which is a key selling point. But even for plugged-in devices, lower power means less heat.
Which means you can use cheaper packaging.
Exactly. You can use plastic packages instead of more expensive ceramic ones. And crucially, you can often eliminate the need for a cooling fan. Fans add cost, noise, points of failure, and they take up space.
And if the device is sealed, like inside an engine compartment or inside a kitchen appliance,
Then heat dissipation is extremely limited. The thermal budget is tiny. This forces the architecture to be incredibly power efficient, just to operate reliably without overheating. We'll see later how they actually measure this with things like performance per watt. Okay, so a huge chunk of the embedded world isn't just controlling things, it's processing signals, right? Audio, video, radio waves, sensor readings. This brings us to a special kind of processor, the digital signal processor, or DSP.
Hmm.
That's right. Many embedded applications are fundamentally about processing information that arrives as a continuous stream of samples, a signal. Think about your phone converting your voice to digital data, or a camera processing light from its sensor.
And DSPs are built specifically for that kind of work.
They're highly optimized for the kinds of math involved in signal processing algorithms, things like filtering noise out of audio, compressing image data, performing fast Fourier transforms, FFTs to analyze frequencies, or discrete cosine transforms, DCTs, used in video compression, like JPEG and MPEG.
So they're not general-purpose number crunchers. They're laser-focused on specific operations.
Very much so. And the absolute king of operations in the DSP world is the multiply accumulate, or MAC.
Multiply accumulate. Okay, what does that do?
It does exactly what it sounds like. It takes two numbers, multiplies them together, and then adds that product to a running total, an accumulator register. So an instruction like MAC A, B, C basically means A equal A plus BC.
And that specific operation is central to all those filtering and transform algorithms.
It's the core computational kernel. It gets executed over and over and over again in tight loops. In fact, DSP performance is often measured almost solely by its MAC throughput, how many millions or billions of MAC operations it can perform per second.
Now, here's something I found really interesting in the sources. Unlike our desktop CPUs that generally use floating point numbers for high-precision math, DSPs often stick with fixed-point arithmetic. Why go backwards, seemingly? Yeah, it seems counterintuitive, but it comes back to those core constraints: cost and power. Floating point units, the hardware needed to handle numbers with moving decimal points, are complex. They take up space on the chip, they burn power.
A lot of space and a fair bit of power. Fixed point is much simpler, hardware-wise. It's like a low-cost floating point. The basic idea is that you just assume the binary point, the equivalent of a decimal point, is in a fixed position. Often is placed right after the sign bit, meaning the numbers represent fractions between -1 and +1.
Okay, but if the binary point is fixed, how do you represent really big or really small numbers? In floating point, the hardware tracks the exponent automatically.
Ah, that's the catch. With fixed point, the hardware doesn't track the exponent. That burden falls entirely on the programmer.
The programmer has to keep track of the magnitude manually.
Manually. It's a technique sometimes called blocked floating point. The programmer has to manage a separate variable that holds the exponent, or scaling factor, for a whole block of data, if calculations start making the numbers too big or too small.
They risk overflowing or losing all precision.
Exactly. So the programmer has to explicitly insert shift instructions into the code to move the bits left or right, effectively moving the implied binary point, to keep the values within the representable range.
Wow, that sounds incredibly difficult and error-prone. It is. DSP programming is a highly specialized skill. You need a deep understanding of the algorithm, the potential range of values at each stage, and how to manage the scaling to avoid overflow while maintaining enough precision. It's a major trade-off. Saves silicon cost and power, but drastically increases software complexity. So given that numbers are constantly being shifted and potentially truncated, how do they avoid losing too much precision, especially in those long chains of MAPC operations?
That's where the DSP architecture compensates. Even if the input data and the multipliers are relatively narrow, say 16 bits wide, which is common for audio samples, the accumulator register, where the sum builds up, is made much, much wider.
Like extra guard bits.
Precisely. For example, a popular DSP family like the Texas Instruments TMS320C55 might use 16-bit or maybe 17-bit inputs for its multipliers, but the accumulator, where the results are summed, is 40 bits wide.
40 bits, so that gives you a huge amount of headroom.
A huge amount. Those extra 24 bits or so act as guard bits, allowing many intermediate MSC results to be added together without overflowing the accumulator, preserving precision through the calculation chain, even with the fixed point representation.
That's a really clever architectural trick to balance the constraints. Let's talk about that TI-320C55 specifically. The sources highlight it as being really optimized for low power.
Yeah, the C55 family was designed squarely for battery-powered devices, like cell phones back in the day. Its architecture is all about maximizing that MS throughput while sipping power. It has, I think, a 7-stage pipeline, and importantly, it features 2 independent MSC units.
2 MZs, so it can do 2 multiply accumulates at the same time.
Parallel, yes. Each one can typically perform a 17-bit by 17-bit multiply and add the result to its own dedicated 40-bit accumulator. When the pipeline is full, it can sustain 2 MSC operations per clock cycle. That's a lot of signal processing punch for a low-power chip.
And how does it handle that cache predictability issue we talked about earlier? Does it have caches?
It does. The C55, for instance, might have a 24 KB instruction cache. And here's the embedded twist. The designer can configure parts of that cache, or maybe all of it, into what they call RAM set mode.
Which sounds like the cache locking we discussed.
Exactly like that. Once code is loaded into a RAM set block, it's locked down. It won't be evicted. So you get the predictability of software-managed memory for your critical code loops, ensuring they meet those hard, real-time deadlines.
And tying back to power again, the C55 does something clever there too, right? With idle domains?
Yes, that's a key feature for battery life. The chip's internal circuitry is divided into different functional blocks: the CPU core, the DMA controllers, various peripherals, the cache, memory interfaces. These are called idle domains.
And you can shut them down individually.
The software can selectively put entire domains into a very low-power idle or sleep state when they're not actively needed for the current task. If you're not using the DMA, power it down. Not accessing peripherals, put them to sleep. This granular control is way beyond what you typically see on a desktop chip and makes a huge difference in stretching battery life in mobile devices.
Okay, so we've talked a lot about low power, low cost, but not all embedded systems are simple controllers. Some need serious horsepower, think high-end network routers, advanced medical imaging, maybe even sophisticated gaming consoles before the PS2.
Absolutely. There's a whole segment of the embedded market that demands very high performance, often exceeding what a traditional DSP can deliver alone. And for these, the sources point to architectures like the Texas Instruments Veloc ITI family, the 320C6X series. And these use an approach that largely lost out on the desktop, very long instruction word, or VLIW.
Right? VLIW is a really interesting choice here. On the desktop, VLIW architectures like Intel's Itanium faced huge challenges and were ultimately overtaken by superscalar designs.
Where the hardware figures out the parallelism on the fly.
Exactly. Superscalar chips have complex logic to look at a stream of regular instructions and dynamically find ones that can be executed in parallel on multiple execution units. VLIW takes a different approach.
It puts the burden on the compiler.
Entirely. In VLIW, the compiler is responsible for finding the parallelism. It bundles multiple independent operations, maybe up to 8, on something like the C6X into a single, very long instruction word. The hardware just takes this bundle and dispatches each operation to a corresponding execution unit. Much simpler hardware.
So why did embedded designers stick with VLIW or choose it when the desktop world moved on? It seems like it must offer some advantages in this context.
It offers several key advantages, all rooted in those embedded constraints. First, code compatibility is much less of an issue.
Because you're not trying to run decades of old software.
Precisely. If a new, faster C6X chip comes out, the company making the router or the medical device can just recompile their specific application for it, maybe do some hand tuning. They don't need to worry about running Microsoft Word from 1995. That backward compatibility burden killed VLIW on the PC.
Okay, that makes sense. What else?
Second, memory latencies are often predictable in embedded systems. We already talked about why hard real-time requires it. VLIW compilers work best when they can predict how long memory access will take, so they can schedule instructions effectively around those latencies. Superscalar tries to hide unpredictable latency. VLIW leverages predictable latency.
And the third reason? I'm guessing cost and power again.
You got it. This is probably the biggest one. VLIW hardware is significantly simpler, smaller, and lower power than superscalar hardware. All that complex dynamic scheduling logic in a superscalar chip. The dependency checking, the instruction reordering buffers, and it consumes a lot of chip area and burns a lot of power.
VLIW just offloads all that work to the compiler.
Exactly. The compiler does the heavy lifting offline. So you save silicon real estate, which means lower cost, and you save power, which is critical. The trade-off is a much more complex compiler, but in the embedded world, that's often a worthwhile trade for a cheaper, cooler running chip. Okay, but VLIW historically had a big downside: code size. If your instruction word has space for 8 operations, but in a particular cycle you only have 2 that can run in parallel, you traditionally had to fill the other 6 slots with NOPs. No operation instructions, just placeholders.
Which makes the code huge. And we just said minimizing code size is vital for saving memory cost. How did the C6X get around that?
They came up with a really elegant solution using what they call instruction packets or execute packets. An execute packet contains a group of instructions that can potentially execute in parallel.
Okay, but here's the clever bit. Each instruction within that packet has a special control bit, often called the pay bit, for parallelism. This bit tells the hardware whether the next instruction in the packet should be executed in parallel with the current one or sequentially in the next clock cycle. So you don't need NOPs to pad out the width. You just signal the end of the parallel group within the packet using that pay bit.
Exactly. It allows them to pack instructions tightly achieving code density very similar to a traditional RISC architecture, effectively neutralizing VLIW's historical code bloat problem. It was a key innovation.
Very clever. And they use other tricks too, like predication.
Yes, the C6X makes heavy use of predication. This means many instructions can be conditionally executed based on the value of a register without needing a traditional branch instruction. This avoids pipeline stalls associated with branches, and it's particularly powerful for optimizing loops, allowing for effective software pipelining, where instructions from different loop iterations overlap execution. Essential for DSP-type algorithms.
Okay, moving beyond pure VLIW DSPs, we also see regular microcontrollers getting DSP-like abilities through things called media extensions, often using SIMD. What's SIMD?
SIMD stands for Single Instruction, Multiple Data. It's a relatively low-cost way to add parallel data processing to a standard processor architecture.
How does it work?
Well, think about multimedia data like the red, green, and blue color values for pixels or samples of an audio waveform. This data is often narrower than the processor's main data path. Maybe you have 8-bit color values, but your main ALU is 64 bits wide.
So you're wasting most of the ALU's width on that single 8-bit operation.
Right. SIMD allows you to partition that wide 64-bit ALU. You can tell a single instruction, like an ADD instruction, to treat the 64-bit operands as, say, 8 separate 8-bit values or 4 16-bit values.
And it performs the addition on all of them simultaneously.
Simultaneously in one clock cycle, usually by disabling the carry propagation between the segments. So one instruction performs multiple operations in parallel on these narrower data types. It's a huge performance boost for things like image processing, video decoding, graphics rendering, without adding a ton of complex hardware. Makes sense.
And one last thing related to this kind of math, saturating arithmetic. The sources mentioned DSPs and media extensions often use this instead of normal arithmetic. Why? Again, it comes back to real-time reliability. In normal arithmetic, if you add two large numbers and the result is too big to fit in the register, you get an overflow.
Which usually triggers an exception, an error flag.
Right. And handling that exception takes time. The processor has to stop what it's doing, jump to an error handling routine.
And potentially miss its real-time deadline.
Exactly. In a hard, real-time system, you often can't afford that interruption. Saturating arithmetic provides an alternative if an operation would result in an overflow.
It just clamps the value. It saturates the result to the maximum or minimum representable value for that data type. So if you're using 8-bit signed numbers, range -128 to +127, you can calculate 100 plus 100. The result isn't an overflow error, it's just clamped to +127.
So the calculation finishes on time even if the answer is technically wrong in that specific case.
Precisely. It sacrifices absolute numerical accuracy in overflow cases to guarantee that the computation always completes predictably and on time. For many signal processing tasks, like audio volume control, a momentary saturation is much less harmful than completely missing a processing deadline. Reliability trumps perfect accuracy.
Okay, we've laid out the constraints: real-time, cost, power, predictability, and some architectural approaches like DSPs and VLAW. Now let's see how these play out in real-world systems. The Sony PlayStation 2 is a legendary example. Its Emotion Engine CPU seems like a poster child for this kind of specialized embedded design.
It absolutely is. The core challenge for the PS2 was handling these massive continuous streams of data graphics, textures, vertex data, audio samples. It needed enormous predictable memory bandwidth.
And its solution was completely different from, say, a PC or server architecture of the time.
Totally different. If you look at a typical server, you usually see a unified main memory system accessed through a common bus with complex cache hierarchies trying to keep data consistent everywhere. The PS2 basically threw that model out the window.
How so?
Instead of one big pool of memory, the PS2 architecture featured at least 9 distinct memory systems and memory controllers.
9. That sounds incredibly fragmented.
It was deliberately fragmented. You had the main 32 megabytes of high-speed DRAM, yes. But then you had specialized memories, like 4 megabytes of embedded DRAM built right onto the graphics synthesizer chip itself.
Okay, why put memory on the graphics chip?
Bandwidth. That embedded DRAM on the graphics synthesizer was connected to the pixel processing logic via an absolutely massive 2048-bit wide internal bus.
2,000 bits wide, compared to maybe 64 or 128 bits on a desktop bus back then?
Exactly. This incredibly wide, dedicated path allowed the graphics chip to read and write pixel data to its local memory at immense speeds without constantly fighting for access to the main system memory bus. It guaranteed the bandwidth needed for filling the screen with complex graphics.
So, fragmenting the memory was key to guaranteeing data flow. And the processing units on the emotion engine were also split up in unusual ways, weren't they? The CPU and the vector units.
Yeah, the design reflected the typical flow of a game. There was the main MIPS-based CPU core, which was tightly coupled with the first vector processing unit, VPU-0. They acted like a team, primarily handling the main game logic, character control, the immediate foreground action.
Okay, CPU plus VPU 0 for the main stuff. What about VP 1?
VPU-1 was different. It was designed more like an independent, specialized vector processor. It could fetch its own instructions and data streams, operating more autonomously. It was often used for background tasks, maybe complex physics simulations, environmental effects, background animation, things that didn't need cycle-by-cycle synchronization with the main CPU. It even had its own dedicated memory spaces.
So you have multiple processors, multiple memories, all running somewhat independently. Who keeps track of making sure the right data is in the right place at the right time? Where's the cache coherency hardware? That's the crucial point. There wasn't much hardware support for automatic coherency like you'd find in a server. The burden fell almost entirely on the programmer. The game developers had to manage data movement manually.
Manually. The PS2 provided, I think, 10 independent direct memory access, or DMA, channels. Programmers had to explicitly set up these DMA transfers to move data between the different memory spaces from main memory to VPU memory, from VPU results back to main memory out to the graphics chip, etc. They used techniques like double buffering extensively.
Wow, so they traded hardware complexity for programmer complexity.
Exactly. They pushed the complexity onto the software team to achieve that guaranteed high-volume data flow needed to hit the real-time target, typically 15 or 30 frames per second, for smooth gameplay. The architecture prioritized predictable data movement over automatic data consistency, a total contrast to general-purpose design. Okay, let's look at another example. A digital camera, like the Sanyo model mentioned in the sources. This seems like a prime candidate for the system-on-a-chip approach. Definitely. The Sanyo VPC SX500 is cited as a great example of an SoC. They integrated pretty much everything onto a single piece of silicon. The main processor core, a dedicated image signal processor for handling the sensor data, memory controllers, interfaces for the LCD screen, the memory card, USB, everything.
And the big win there is
Size reduction, obviously, for a compact camera, but also, crucially, power reduction. By integrating everything and eliminating off-chip communication where possible, they dramatically cut power consumption. Sanyo claimed, I believe, that this SoC allowed the camera to run on half the number of batteries compared to previous models using multiple chips.
That's a huge selling point for a portable device. And even within that single chip, they still didn't just use one big internal bus, right?
That's another key embedded technique. Because you have devices with vastly different speed requirements all on the same chip, using one bus becomes a bottleneck. So the Sanyo SoC used multiple internal buses.
Like different highways for different speeds.
Sort of. There might be a relatively slow, maybe 16-bit wide bus connecting to low-speed peripherals like the memory card interface or control buttons, but then a separate, much faster, maybe 32-bit wide bus connecting the performance-critical components, the main CPU core, the image processor, and the main SDRAM memory. Segmenting the buses helps ensure the high-speed components get the bandwidth they need without being held up by slower devices. Makes sense. Okay, final case study. The cell phone. You mentioned earlier, by 1999, more cell phones were being sold than PCs. And inside these devices, it's basically a specialized mobile computer. It really is. And the core design, especially back then, relied on a dual processor approach. Because a cell phone is fundamentally a computer that also has to act as a sophisticated radio.
So you need one brain for the computer stuff and one for the radio stuff.
Pretty much. You typically have a DSP, a digital signal processor, whose main job is handling the radio signals. That includes the heavy math for compressing and decompressing your voice, like GSM or CDMA codecs, plus managing the actual radio frequency functions, amplifying, filtering, mixing the signals.
Okay, DSP handles the signal pass. What's the other processor?
The other is a general-purpose microcontroller. This one runs the phone's operating system, manages the user interface, the keyboard, the display handles power management, controls the battery charging, and, critically, orchestrates the communication protocols with the cell tower, setting up calls, handling handoffs, etc.
So they split the tasks for maximum efficiency. The DSP does the heavy signal math. The microcontroller does the control and coordination.
Exactly. Let each processor do its best at.
The sources also mention the wireless standard itself, specifically CDMA, code division multiple access, having an impact on the design, particularly battery life. How did that work?
CDMA was a newer digital standard compared to older analog ones like AMPS or even early digital like KDMA GSM. In CDMA, many users share the same wide frequency bands simultaneously.
How do they not interfere with each other?
Each call is assigned a unique pseudo-random code. The receiver uses that code to pick out the desired signal from the background noise of all the others. It's a bit like everyone talking in a crowded room,
Right.
but you can only understand the person speaking your unique code language.
Okay, and the benefit.
Well, first, it significantly increased network capacity compared to older systems. But for the phone itself, a key aspect of CDMA is power control. To make the system work, the cell tower constantly tells each phone exactly how much power it needs to transmit at.
Why?
If you're close to the tower, you need to transmit at very low power. Otherwise, you drown out signals from people farther away. If you're far away, you transmit at higher power. This constant, tight regulation means that, on average, CDMA phones transmitted at significantly lower power levels than older phones.
And lower transmission power directly equals.
Longer battery life.
Okay.
Plus, the spread spectrum nature encoding also offered better call quality and privacy compared to older analog systems.
So we've seen this incredible diversity in architectures. DSPs focused on MX, VLIW chasing parallelism, tiny microcontrollers minimizing cost, complex SoCs. How on earth do you benchmark these things? It's not like running Cinebench on a microwave controller, right?
No, definitely not. The sheer variety of applications and performance goals makes standardized benchmarking incredibly difficult. You have hard real-time deadlines in one application, soft real-time in another, pure cost-performance optimization in a third. A single benchmark suite just can't capture all that.
So what did they do? The sources mentioned some manufacturers were still quoting Tristone numbers.
Yeah, for a long time the industry struggled. Tristone is an old, tiny integer benchmark that the desktop world had largely dismissed as irrelevant decades ago because it's so easily gamed and doesn't represent real workloads. But some embedded vendors kept using it, mostly for lack of a better alternative.
Until the industry came together.
Exactly. Eventually, the EDN Embedded Microprocessor Benchmark Consortium, or EEMBC, pronounced Embassy, was formed. Their goal was to create relevant, credible benchmarks for the embedded space.
And what did they come up with?
EMBC developed a suite of benchmarks based on algorithms and code kernels actually used in real embedded applications. They grouped them into different application classes.
Right.
I think there were originally 5 or 6, covering areas like automotive industrial, networking, telecommunications, office automation, and consumer electronics, like digital entertainment.
So an engineer could pick the benchmark suite most relevant to their specific field.
Precisely. They could compare processors using benchmarks that reflected tasks like routing packets, filtering signals, or compressing data, rather than some abstract score like Drystone. Gave a much more meaningful comparison for specific application domains.
But even with relevant performance scores, we keep saying that raw speed isn't the main goal here. It's about efficiency.
Absolutely.
Yeah.
And EMBC recognized this too. They introduced an optional component called Energy Bench, which produces an energy mark score.
Measuring power consumption while running the performance tests.
Exactly. It measures the energy consumed to complete a specific workload from the performance benchmark suite. This finally allowed for a standardized way to quantify what everyone in the industry knew was critical, performance per watt. And when you look at those performance per watt numbers, the results really highlight the design philosophy, don't they?
They absolutely do. The sources give a great example with an NEC processor, the VR4122. If you just looked at its raw performance scores on the EMBC benchmarks, it was often near the bottom of the pack, second slowest, I think, in some comparison.
Okay, so not a speed demon.
Not at all. But when you looked at its energy mark scores, performance per watt, it was the big winner, completely dominating the efficiency rankings. Because it was designed specifically for battery-powered mobile systems, its entire architecture was optimized for sipping power. And its success in the efficiency metric proved that, for its target market, achieving good enough performance within incredibly tight power constraints was far more valuable than just winning a raw speed race. It perfectly encapsulates the embedded design trade-off. Cost, size, and efficiency often matter much more than peak theoretical performance. Okay, so let's try and wrap this up. We started out talking about this invisible empire of computing all around us. And what we found is that this empire is built on a foundation that's almost the opposite of the desktop world we know.
It really is. The absolute obsession is with guaranteed, predictable performance, meaning that worst-case execution time often driven by hard, real-time deadlines. And achieving that predictability, along with minimizing cost and power, forces designers to make radical choices.
Like rejecting the very things that give us speed on the desktop.
Rejecting or fundamentally changing them. getting rid of complex dynamic branch prediction, replacing dynamic caches with software-managed memories or lockable caches, embracing VLIW over superscalar to save power and area using specialized DSPs.
And even fragmenting the whole system architecture like we saw on the PlayStation 2 with all those separate memories and DMA channels managed by the programmer.
Yeah, the PS2 is such a prime example. That architecture prioritized guaranteed high data flow for continuous media streams. Even if it meant sacrificing the data consistency mechanisms and programmer convenience we expect in general-purpose systems like servers, which are optimized for mostly static data. It's a world where reliability under deadline pressure, efficiency, and cost rule everything.
It's a completely different way of thinking about computer architecture, driven by totally different pressures.
Fascinating set of trade-offs, really. Constraint breeding some serious ingenuity.
It really is. And that leads us perfectly into our closing thought for you, the listener. We've seen how the features that make embedded tech reliable, maybe that smooth frame rate on your old console or the clear audio processing on your phone, were often achieved because designers removed or worked around the high-performance but unpredictable features from desktop chips, like dynamic caches or speculation. So think about the computer you use every day, your laptop or desktop. What other features does it have, features you rely on for its speed and responsiveness, that you suspect would completely fail if subjected to a strict hard, real-time deadline test? Something to ponder.
Thanks for joining us for this deep dive.
We'll see you next time.